In this lecture, we will be talking about Newton's laws of motion, Newton's 3 laws of motion. They're fundamental to physics. It's a really exciting chapter for me to talk about. And unlike last chapter where we had to specify that the equations only applied to constant acceleration, well, these do not. But what they don't apply to is things that are very small or very fast and small. But all macro scale things that you see in the everyday world, these laws of motion apply to. So up till now, we've been learning how to describe motion. That's what we would call kinematics, specifically with constant acceleration. But we haven't been giving much consideration to the cause of this motion. At best, we say that a projectile, is shot out of a cannon or thrown. But we consider once it's in free fall, that's what we're considering with our projectiles. We're not really considering what gave it its motion in the first place, this cannon. And we're considering gravity as an acceleration and nothing else. We were ignoring wind resistance and all the like. And so what would happen if instead we wanted to analyze, say, just a box on the ground that we were pushing? So this is maybe a hand. That's a thumb. That we were pushing. So we were exerting a force on it. It would certainly be put into motion, and we can analyze that motion, velocity, as an acceleration as time goes on, right? Those are the tools that we have. But what is this this term force that we use loosely in everyday language? What is it specifically in physics? So Newton's laws of motion, or Newton's 3 laws, will help us figure all of this out. So let me go to the brush that I know shows up better here. Marker. So a force is an interaction between one body and another, or between a body and its environment. So force, and we usually abbreviate that F. And force is a vector, we will see. So it's an interaction between one body and another, between a body and its environment. So the hand pushing the box, or the projectile shooting the cannon shooting the projectile. So forces can be contact or non-contact, right? So gravity is an example of a non-contact force. Also, magnetic forces are an example of non-contact force. If you ever hold two bar magnets up against each other and you feel an attraction or a repulsion, then you would be experiencing non-contact force. But largely what we will be concerned with is contact forces, except for gravity. So we can have, there's a few common forces that we'll experience. There's push or pull kind of force. There's a normal force. There's a tension force. So let me draw 5 common forces here. So I had the push type. So we have a box here as an example. And you're just applying some sort of a push. This is supposed to be a hand. It kind of looks like a foot to me. You could have a foot with a thumb on it, and it could still apply a force, I guess, right? So there's some force being applied to this box because we're pushing it. There's also, so here, this is like a push force. There's also normal force. So this is the force that a surface that an object is resting on exerts on that object. And if you're unfamiliar with this phenomenon, we will talk about it. It's one of Newton's 3 laws. So don't feel too confused by this one. Normal force. We have, let me scoot this guy over here. We have a frictional force, right? So let's say we could just extend this whole thing. Could be multiple boxes on the ground here. Frictional force, so if this box were moving this way, actually, oops, it doesn't even have to be moving, there's static and forces, but anyhow, frictional force acts in the opposite direction from the motion, so this would be frictional. Frictional. And then 2 more. Tension. Yeah. One big long road here. Here's our box. And we have maybe a string that's being pulled this way here. So there's some force vector. I did the same thing. This way. And this is a string that somebody's holding on to. Let's see. Yeah. They're pulling it. So this would be a tension. Force. And gravitational force, which is really all that we've alluded to up till this point. So gravitational pulling that way. Yeah, gravitational, that works. Okay, so we assign these things certain specific subscripts. So friction, you would give this little fancy f, or you can just write it as a fancy f vector. A lot of books do it this way. A lot of students find that to be pretty convenient. This one is a normal force, and so we do a capital N as a subscript, or you can just do one big capital N as a vector, and that would be understood to be the normal force vector. For tension, F with a big T, capital T underneath it, or just capital T here. And then for gravitational, you can write Fg, or you can write weight, I guess. That's seen in some textbooks, so W. Or you can write mg, which alludes to what we will cover in the future. All right, so these are 5 common forces. There are many other forces, but these are the common ones that you'll be working with here. So, there's a principle called superposition of forces. It's kind of a mathematical thing with vectors. So superposition of vectors. It just means that the total force applied at any point on a body is equal to the vector sum of all the forces at that point. So, for instance, if we have something with lots of forces being applied to it, so let's say it has gravity being applied, it has a normal force, it has somebody pushing it, and somebody pulling it this way, right? You can find the vector sum of all of those forces and find the one resulting force vector. I don't know which way it would be exactly, depends on the magnitude, but judging by the lengths of them, maybe something like that. And we'll call that r here. Let's just call that the vector sum of all the forces, just as an example. And so r, you can say, is equal to F1 plus F2, the other force, plus F3, another force, and so on. Right? So it's equal to, in other words, the sum of all the forces, the vector sum specifically. Right? So in this case, this would be like F1 and F2 and F3, doesn't matter the order, and so on. So this is helpful in multiple ways. This is helpful in two ways, I'll say. For one, we can take all of these and we can add it up to the one single resulting force vector. That's useful, so you know which way the acceleration, the final acceleration on the object is actually being applied, which direction the acceleration is. But also it means that, like for example, in this one we have this weird tension force that we identified. And if this is our x direction, for example, and this is our y direction, which will probably commonly be the case, we can break this guy up into its x and y components. And it is equal to the sum of its vector, of the component vectors, of its component vectors. And so we can take multiple full vectors and add them up to find the total resulting vector, or we can break down vectors into their components to analyze on an axis by axis basis what's going on with our forces and therefore accelerations. So, for example, I'll go back to this color here. So our x would be equal to the sum of all the forces in the x, right? So the x component of this resulting vector, we were talking that component, right, is the result of all the x component, the x components of all of the forces. And our y is equal to the sum of all of the y components of the forces. And if you had 3 dimensions, it could go z as well, of course. F, z. And so therefore, r as a total magnitude is the square root of the squares of all of these individual components. R z squared. Z. All right. So it's really an incredibly powerful strategy to consider the sum of the forces in component form and the x and the y separately. That is basically the strategy for these problems, is to consider all the forces in the x, consider all the forces in the y, and go from there. So, quick example here. Let's say that we have, do this. So let's say we have children playing on a Ouija board where they all hold this little wooden thing, the circle through it, and it hovers over a game board with letters on it, right? A, B, C. And it's just kind of a superstition game, and everybody, all their hands are on it from different angles, and nobody's thinking that they're moving anything, but eventually these are supposed to be hands. But eventually the thing ends up moving because somebody has the jitters, and it's kind of a creepy game for children. So let's say children are playing this game, and that wooden piece is called the planchet. I had to look that up. That's interesting. The forces on the planchet are as follows. So here we have, let's say I'll give you this x and y axes. So this is x, and this is y. Oops, positive y here. Okay? And then here we have the planchet. I'll draw it out there like that. And its center of mass would be right at the origin. So you have one child exerting a force vector on this that is like this. So we'll call that F1. And it makes an angle here, 40 degrees. Psi equals 40 degrees. You have another child that is exerting a force vector with their hands down this way. I should probably draw these vectors a different color because it's overlapping, but you'll be able to see with the arrows. This is F2. And then you have a third that is exerting it this way, directly along the x. And this is F3. All right. And the magnitudes of F1, 2, and 3 are right here. F1 is equal to 2.0 newtons. F2 is equal to 1.5 newtons. And F3 is equal to 4.0 newtons. Newtons is the unit of force. It's named after Isaac Newton, Newton's laws of motion. He came up with some of these ideas, and so there you have it. A newton, by the way, as a unit, is equal to a kilogram times a meter per second squared. That is a newton. It's worth jotting down. It's worth remembering. So anyways, we have magnitudes of these forces. We have directions, right? A couple of them are right along the axes, so those are kind of easy. And then this one we have on some angle off of the horizontal, right? So what we want to find, find Rx, right, the total resulting force vector, x component of the resulting force vector, which is equal to, so that's supposed to be a sum sign, which, by the way, as a reminder, is equal to F, sum of the forces in the x. Likewise, we're going to find Ry and Rz, right? And we are going to find also theta, we'll call it theta, which is the resulting angle of R, right? So the angle of the resulting sum of all of the force vectors. So to do this, we look at the sum of the forces in the x and the sum of the forces in the y. So we're going to look at the sum of the forces in the x is equal to something. And over here, I like to do x on the left, y on the right, and you can kind of carry out this format if it works for you for a lot of problems. Sum of the forces in the y is equal to something. Yeah. So, sum of the forces in the x. Well, we have this one, which is clearly in the negative x direction. So we definitely have that, but we also have this component of F1, right? It's partially in the x direction and partially in the y direction, right? So this here would be the part of it that's in the x. So I'm going to say fx1, and this here is the part of it that is in the y. So, oops, not x. Yeah, f1x, f1y. f1y. So we have to consider the components of each, right? If we ignore it, we're ignoring this force F1's contribution in the x direction. So we have to include it. So that means that over here we have what do we call it? F1x minus, because this is in the positive x direction, and then F3 is in the negative x direction. So there we have it. Hopefully I'm not cutting off too much. Try to write large enough so that it shows up fine on the screen, but so that you're not missing anything. I could scoot this guy over just a little bit. There. Maybe that's better. Alright, and then in the y, what do we have? In the y, similar story. We have one that's directly in the negative y direction. That would be F2. But we also have a component of F1 that is in the positive y direction. So we have F1y minus F2. Yeah? And so now we can quantify these things. So F1x, if this is our angle, is equal to F1 cosine psi. If you follow that immediately, you're in great shape. If you don't, you really ought to gain some practice. Go back to previous lectures or chapters if you have to. But this is something that you will want to be able to translate really fast going forward in physics. When you're breaking a vector up into components, you don't want to have to think too hard with too many steps about how I got this component here, right? But cosine phi is equal to this f1x over, so adjacent over hypotenuse, over f1. And so then if you just bring this guy on over, then you have f1x. And so we've substituted f1x. But you really don't want to have to go through all those steps every single time you come up with the x and y component of a vector. You want to just think of cosine as x and sine as y, and just kind of have this in your mind. And then that's minus f3. So here, what would this be? So f1y, well, it's going to be f1 times sine this time of phi. That is the y component of that vector. It should be really that fast for you pretty soon, if it isn't already. Minus f2, the full vector f2. All right, and we have all this information. So we're given f1, 2, and 3 magnitudes, and we're given what psi is. So we have everything we need. So we can just plug in. So f1 magnitude is 2 newtons times cosine of, what was it, 40 degrees, I think? Yes. Yes. Minus f3 is 4 newtons. And if you plug all of that in, then you get that Rx, right? Rx, which is equal to the sum of the forces in the x, is equal to minus 2.5 newtons. Minus 2.5 newtons. Alright, so that was one of the answers we were wanting to come up with, so I'll box it in. And then this one, plug it in, same way, and you should get that Ry is equal to negative 0.2 newtons. So they're both negative. You should preserve those negatives. They are important. They tell you about direction. So now, if we are wanting to get the magnitude of R, I guess I didn't write that down up top here, but that is another thing I wanted you to solve for, is the magnitude of R. Then you would just do the square root of the squares, square root of the sum of the squares of the components, right? So Rx, this kind of looks like a y from your angle, I think, squared plus Ry squared. And if you plug that in, you should get 2.5 newtons. That would be R, the magnitude of the resulting force vector. And then if you want to find the angle of R, so I kind of denoted it this way, that would be equal to the inverse tangent of Ry over Rx. Right? Why is that? Where did that come from exactly? Well, you have a resulting force vector. This is R. And you have an axis, right, that belongs to. Right? This is x, and this is y. And so therefore you have two components to this R, right? Components, components, components. Right? So there's Rx and Ry, and it makes some angle. I'm calling this problem theta. And so if you want to find the angle, and you have Rx and you have Ry, that would be the tangent of the angle. So that's where you get that formula. All right. So if you plug this in, what your calculator spits out is 4.6 degrees. Make sure always that you're either in degrees or radians, whatever you're intending to work with. But 4.6 degrees, okay. So our Rx was negative, and our Ry was negative. So the resulting force vector is somewhere in this quadrant. We know, because both our x and our y are negative. So it's this way in the x, and this way in the y a little bit. So it's going to be somewhere over here, right? Does that make sense? And so our theta coming out of this inverse tangent from our calculator of 4.6, that's not 4.6 degrees. 4.6 degrees would be something like this. We know that's not right. Like we know that that is not right. So you have to consider the quadrant. So since we know that it's in quadrant 3 here, then we know to add 180 degrees to this, right? And so it would be 180 plus 4.6 to get it in the right quadrant. This is something you no doubt remember from your trig class, that the calculator doesn't always spit out the right number. You have to think about what quadrant you're working with. So theta r is really equal to 180 plus our resulting 4.6 that we got. So 184.6 degrees. That is really the angle. And so the planchet on this Ouija board, the little wooden thing with all these 3 children moving it without realizing it, it goes somewhere in this direction. And that's because the force vector F3 was by far the largest. So there we have it. Some vector math superposition of forces and force vectors. All right, that's it for this video.